All right, hi everyone. I'm going to present my talk on SG2VID from TU Darmstadt today. So conventional surgical training is essentially based on the Halstead model of see one, do one, train one, where you first watch and learn from an attending surgeon, then under their supervision, you would directly practice that surgery on a patient. So this obviously raises major ethical concern, but also logistical problem, but at the same time it's directly linked to suboptimal patient outcome due to the lack of experience of novice surgeons in handling complications. In fact, it has been shown that surgical harm causes more global mortality than all of the infectious disease combined. So how could we address this problem and accelerate their learning curve way before they start their surgical practice? First, we could give them access to surgical simulation tools that are realistic and patient-specific, which current state-of-the-art tools still lack of. Second, we can show them even more diverse set of surgical videos performed all around the world as part of learning material. However, sharing these materials are usually difficult due to lack of patient consent and also privacy regulations. And finally, we can show them even more examples of rare cases and complications that are really hard to come by so that they know what to look for and what to prepare for them. So generative models have been proposed to handle some of these issues to some extent, but there are still some major limitations that I will explain next. And then in the second half of my talk, I will show you how SG2VID, so our model, can address each of these problems here. So to control generative models, it was proposed initially to use simple conditioning signals like class labels, later extended to trajectories, or even full-on text prompts. However, they don't really give you the ability to precisely synthesize the same. So, for example, which direction you want to bring a tool in, how fast, which angle, and so on. So you need to keep running this prompt engineering cycle and keep adding more detail to the prompt until you achieve what you want. So the community understood the problem and started shifting towards more complex conditioning signals like depth map, optical flow, and even segmentation mask. However, this would directly trade off the human controllability aspect that text prompts had. So let's say I want to bring in a new tool, move it to somewhere else. I have to completely redraw the segmentation mask to synthesize the scene. So this is even more harder to do for videos, of course. So this is where we come in, and we hypothesize that scene graph can actually achieve both without trading off too much. They are compact and human-readable representation of the surgical scene, but at the same time, they allow precise synthesis at the level of segmentation mask. But let me first show you how we are forming our scene graph. So we're going to use segmentation mask to identify connected components and give each of the connected component a node. And then if they are spatially adjacent, then we're also going to give an edge between them. Now they have seen the scene graph. I also want to mention that each of the node is going to contain information such as the class label. It also has two-dimensional spatial spreading. Two-dimensional spatial spreading is height and width, and another two-dimensional centroid position. And then on top, due to video synthesis, we're also going to add one-dimensional average depth, so the average on the component's area, and another two-dimensional average flow or optical flow. And then we're going to apply this on all the frames, extract all the scene graph, and then together with our SG2VID model, we'll be able to achieve precise video synthesis. So throughout this talk, you're going to see two types of results. The first, conditions on first frame, and also the scene graph, and then the second, just conditions on scene graph alone. But let's interpret these results a bit more in depth. So what you're seeing right now are some real videos from Cataract 1K dataset. And when we provide SG2VID, the scene graph, and also the initial frame, it will be able to synthesize the rest of the frame with precise tool and anatomy movement. The size, speed, time, direction, everything matches quite well. We can even bring in a new tool, like in the fourth column there, and it will still bring them the right time, right direction, and so on. You could also do this just on scene graphs alone, and the results would be somewhat akin to generative augmentation, where you see variations in bleeding pattern, variations in eye color, lighting. So this information aren't part of the scene graph itself, which is why you see these variations in them. But yet, the tool anatomy movement that is in the scene graph still matches quite well, or precisely to ground truth. We also performed our experiments, or most of our experiments, on Collect 80 and Cataracts dataset, so all, 3 datasets altogether. But I'm skipping these results due to time limitation. Just wanted to point out some of the interesting generative augmentation that was happening on some of our samples. All right, now let me very briefly explain the architecture of SG2VID. I'm going to simplify quite a bit, so please visit by my poster if you want to know more details about it. Essentially, we're training 2 separate graph encoders, and then use the embeddings from it to train our video diffusion model. And the first graph encoder is going to learn the local textural information, and we're going to do this by just randomly masking out certain components, and then it is tasked to reconstruct the masked component area using the information from the scene graph. The second graph encoder is going to learn the global information, so such as the overall layout, tool tissue interactions happening in the scene, and so on. And we do this by contrastive learning approach between the scene graph and also the segmentation mask. So essentially, it is tasked to guess which scene graph belongs to which segmentation mask. And then using the embeddings from the graph encoder, we are going to train our video diffusion model. So we are just using vanilla diffusion model here or video diffusion model here, but you can plug in pretty much any models. We performed quite a bit of an extensive qualitative-quantitative comparison on all 3 data sets. Essentially, yeah, we were shown to do the best in terms of visual fidelity, not so important, but most importantly, we were shown to do or shown to follow the conditioning most faithfully compared to all the other state-of-the-art methods, which means we are following the tool and tissue movements more faithfully. All right, now let's look into a couple of interesting applications of SG2VID and try to address the problem that I had mentioned earlier. Let's say you're a surgeon and you have a bunch of surgical videos that you want to share to the world, either to get some feedback or even to show your technique. But you don't have proper patient consent on them, so you can't share them due to privacy regulations. What if you could just extract the scene graph, which don't really contain any patient-specific information, and share the scene graph instead? And the surgeons on the other side of the world can just use the scene graph to reconstruct the videos on set of eye images that they do have consent on. But obviously for this to work well, it also needs to generalize well, because surgical videos usually tend to have some sort of shift between different clinical centers. So let's see how they do on that. What we did is we collected a couple of images from a new off-net data set, which is essentially just collection of YouTube videos, and they contain random layout, text, even music playing in the background. So they are overall as out of domain as possible. And then on top, these images, they weren't seen by our model at all. So at any stage, so the graph encoder, autoencoder, video diffusion model, none of them have seen them before. They were only trained on Ghazaei 1K videos. And then we are going to select a couple of Ghazaei 1K video randomly and use their scene graph for the synthesis. Ideally, what you want to see in the output is tool and anatomy movement from Ghazaei 1K, but in the style of off-net image. And these were the results. So as you can see, the tool and anatomy movement precisely follow Ghazaei 1K, but still remain in the style of off-net image. And you can even synthesize global movement, like in the third column there, and you will still do them quite well. So we hypothesized that they do so well because the learned representation is not appearance-based, but rather structure-based, which is also transferable across different domains. And essentially, we disentangle how something moves to what it would look like. And yeah, you could also already think of potential application on unpaired video domain transfer ideas as well, if you do include these videos in your training set, or off-net videos in your training. And finally, we were also able to use the human controllability aspect of SG2VID to synthesize rare sequences of sudden pupil contraction. So these sequences are extremely rare and can cause quite a bit of complication, especially when the tool is deep inside and the sudden contraction causes the tool to hit the iris wall. But we can easily synthesize such sequences. All we have to do is change two value, so the height and width value in the spatial spreading in the pupil node of the final scene graph, interpolate the rest of the value, use the new scene graph to synthesize such sequences. And what you're seeing right now is the tool and anatomy movement precisely still follows everything, just the pupil itself contracts quite rapidly. So finally, yeah, please come by my poster if you're not hangover after the gala night, I guess. You can also follow me on LinkedIn. You can go to the project page if you want to see the videos again and again. We have more examples in the project page. And we have put out everything in our code base, so the model weight, the process data, the code, everything is there. We try to make it as reproducible as possible. So thank you.